Let's continue. In the last few videos, we looked at prime ideals, maximal ideals, and an important class of rings called integral domains. So today's video, I'll start with a quick introduction to field of fractions. Of an integral domain. So this is a very important concept. It's very easy to define this, and the primary focus of this video is actually going to be Noetherian rings that I will define soon, but I want to quickly introduce the notion of field of fractions of an integral domain. So before I define this in general for an integral domain, let's recall the construction of rational numbers from the ring of integers. So Z, remember Q is all elements of this form where M and N are in Z and N is not 0. So I want to express Q as somehow coming from Z. So Q is really set of ratios of integers. So you take integers and you take their ratios and all possible ratios. So you get Q. And what is happening in this process is, what you started with, Z is not a ring, not a field. Right? We started with something that's not a field, but what we obtain is a field. That is a crucial point that I want to emphasize. Z is not a field because it does not contain all ratios, right, in some sense. Because for example 2, which is an integer, does not have a multiplicative inverse. If it was there, it would be 1 by 2. So how do you introduce an inverse for 2? You simply add 1 by 2 to your set. So similarly you add 2 by 3, you add 100 by 141 for example. So you can add all ratios, and Z is of course sitting inside Q, as N is essentially thought of as N by 1. So you have a integral domain which is not a field, and you have introduced all the ratios into that set and made it a field. So now this process can be generalized to any integral domain. So this is what I want to explain now, and the process is exactly the same. So let R be an integral domain. Let's recall quickly what is an integral domain. An integral domain is, so in other words, so if A comma B are in R and AB is 0, then A is 0 or B is 0, right? So every time you have a pair of elements from the ring whose product is 0, then one of them must be 0. This is an integral domain. We construct or we define a field, let's denote that by K, which contains R as follows. So I'm going to define a field which is going to be a bigger ring. In other words, it contains R as follows. So the model is construction of Z, Q from R, from Z. So that's the model you have to keep in mind. Exactly the same model I am following for all integral domains. So how do we define K? This is simply exactly as in the case of rational numbers from integers. We take all ratios. And of course, we do not want B to be 0. We don't want to write something by 0. So we take all possible ratios of elements of R and call that as set K. So K is by definition this. So now I want to make K a field. First of all, we have to define two operations on it, addition, and it is exactly what you would expect that you are familiar with rational numbers. So if you have two ratios, how do you add them? You simply add them like this. And what is multiplication? This is simply A by B times C by D is AC by BD. And here is where you see that it is important to assume R is an integral domain. Right? You see that, because if it is not, otherwise BD can be 0, and then we will have a problem. We have B and D are non-zero, right? These are non-zero. This is not equal to 0, this is not equal to 0, because we are considering two elements of K. So A by B and C by D are elements of K, that means B and D are not 0. In order to define the sum and product, we need this also to be non-zero, and this is what integral domain guarantees us. So we assume that we are working with an integral domain, and this is a very easy exercise now to check that with these operations. K is in fact not just a ring, but it is a field, and this is an easy exercise. Okay, so I will not do this, I will let you check this. You can check that every element has, under the addition, in fact you have an abelian group. Under multiplication also every non-zero element has an inverse, certainly, because you take A by B, if A is non-zero, B by A is also an element of K, so A by B times B by A is 1. So it's in fact a field. And this is an important definition now. K is called the field of fractions of R. Okay, the name is very suggestive, right? It is field of fractions, means it contains all fractions of elements of R. In some sense, it is the smallest field that contains R. Of course, if R is a field to begin with, its fraction field is the R itself. So I will now write quickly some examples. Okay, so one, if R is a field, so let's denote the field of fractions by FF of R. Okay, just for simplicity, field of fractions, FF stands for field of fractions. If R is a field, already R is a field, what is the field of fractions of R? It is just R, right? Because you take fractions of elements of R, they are elements of R again, because R is a field. A by B, if A and B are in R, 1 by B is in R, and B is non-zero, then 1 by B is in R because R is a field. So A is in R, 1 by B is in R, so A times 1 by B is in R. So you get nothing new. This is also confirms what I said. Field of fractions is smallest field, the smallest field containing a ring. So if R is a field to begin with, you should not get anything bigger. So its field of fractions is itself. And the model that I mentioned, field of fractions of Z is of course Q. And following the first example, field of fractions of R is R, field of fractions of complex numbers is complex numbers, field of fractions of Q is Q. What is field of fractions of Z mod 5Z? Z mod 5Z, remember, is already a field, so it's equal to itself. Some other examples, what is the field of fractions of, let's say, polynomial ring in 2 variables? This is important for us. Maybe I should first do the 1 variable case. So So you take polynomials over one field R, real numbers. So then this is what I will denote by R round bracket X. This is called field of, this is the first time I am introducing this. This is a very important field. This is called field of rational functions in one variable X. Okay, this consists of, by the definition of fraction field, all ratios of polynomials. So fx, gx are polynomials in Rx with of course gx non-zero. Okay, so actually I should go back to the definition of fraction field. I should have mentioned this carefully. Remember that two fractions can be same. We say that a by b can equal c by d if ad is equal to bc. So we are not looking at all ratios or all fractions directly. We are looking at fractions under this equality. So of course this is something that you are familiar with, right? In the case of rational numbers, you have 2 by 4 is not considered a different fraction than 1 by 2. 2 by 4 is same as 1 by 2. So you can, in the case of rational numbers, you can cancel common factors. So in general, we want to insist that I don't consider any fractions that we may be able to write as equal, as unequal. If they have this property that AD is equal to BC, I will consider them as same. Similarly here, any ratio I write of fx divided by gx will not give me a distinct element. They could give me same elements. So this is an important field for us. So now of course you can figure out the notation for, let's say I have a polynomial ring in n variables. What is its fraction field or field of fractions? It is simply, I replace square brackets by round brackets, right? Square brackets are replaced by round brackets, and that of course is not just a symbol, it carries a deep meaning, which is that here I am looking at only polynomials in the polynomial ring. Here I am looking at ratios of polynomials. Now what is the field of fractions of Z? Polynomial ring over the integers. Of course you have to put round brackets, in other words you have to take ratios of polynomials, but you also have to at the same time take ratios of integers, because integers are already inside the polynomial ring as constant polynomials. So you have to take q. Z square bracket x1 through xn is q round bracket x1 through xn. One more example. What is the fraction field of Z adjoined 1 by 2? Remember, Z adjoined 1 by 2 from one of the beginning videos in this course. So recall, Z adjoined 1 by 2 is the smallest subring of Q containing 1 by 2. Remember, it already, any subring of Q contains Z, because a subring of Q is by definition a ring, so it contains 1. Once it contains 1, it contains every integer n. So every subring of Q contains Z, but it need not contain 1 by 2. If it contains 1 by 2, we look at all subrings that contain 1 by 2 and look at the smallest one. And explicitly, elements of this ring look like, you have to take essentially polynomials. That's why we are using this square bracket notation to suggest polynomial rings. So we have an 1 by 2 power n, an minus 1 1 by 2 power n minus 1. Think of this as polynomials in 1 by 2, where a0, an through a0 are integers. Okay, so that's the ring. So now, what is, it's an integral domain. because for example it is contained in Q, any subring of an integral domain is an integral domain. So Q is a field, so it's an integral domain. So Z adjoint 1 by 2 is also an integral domain. What is its field of fractions? Now you think about it a little bit. You want to add all ratios of elements of Z 1 by 2. But in particular you have to add ratios of elements of Z. So that forces you to contain Q. And now you don't get any new elements by introducing ratios of 1 by 2. So the field of fractions of Z adjoint 1 by 2 is Q. And I'll finally mention this example. What is the fraction field of Z adjoint I? Okay, Z adjoint I, where I is a square root of -1 as always. Z adjoint I is simply defined exactly as the case of Z adjoint 1 by 2. Of course, now we have to define it to be the subring, the smallest subring of C, the complex numbers containing I, because we can't take smallest subring of Q containing I because Q does not contain I. So what is the smallest subring of C that contains I is precisely Zi. In fact, as polynomials, Zi has a much easier description. This is of the form A plus IB, where A and B are in Z. Because remember, we don't need to take all powers of I and I power 0 are enough, because I squared is -1, I cubed is I power 4th is 1, and so on. So when you take polynomials, you just take this. And what is the quotient fraction field? I claim that you have to, of course, take Q, because you have to take fractions of elements of Z, and then you can put either square bracket, meaning all polynomials, okay? So, or you can put round bracket. These happen to be the same. So now I will mention that this will be described in future. So these are equal. This example is important, and we will come back to this when we talk about fields. Okay, so for now I will leave at least as an exercise for you to convince yourself that field of fractions of Zi is Qi, and once you add I claim that 1 by I is already there, and 1 by I squared is already there, and so on. So that allows you to explain why Q square bracket I is same as Q round bracket I. But this is looking ahead. It's not that important. If you don't understand this at this point, it's okay, and we will come back to this. So that's all I want to say for now about field of fractions. So field of fractions is an important construction for us, especially when we talk about in the future when we talk about fields. And actually one final comment I want to make is that if R is not an integral domain, we cannot define field of fractions of R. Right? So of course the definition that I was giving for you earlier, where I define all ratios or all fractions and add them or multiply them in this fashion, clearly will not work, because product of two non-zero elements in a non-integral domain can be 0. So if R is not an integral domain, in other words, there exist two elements B comma D such that B and D are non-zero, but the product is 0. So 1 by B and 1 by D, you can't define their sum or product. But maybe there is some other way to define field of fractions. Maybe there is some other way to put R inside a field. But this remark is saying that that cannot be done. This is because a subring of an integral domain is also an integral domain. Right? Suppose you could put R inside a field. R is inside a field K. K is actually a field, so it's an integral domain. R being a subring of K is an integral domain, but that of course is a violation of the assumption that R is not an integral domain. So if something is not an integral domain, certainly we cannot define its field of fractions. Okay, so that's so much about field of fractions. Next, I want to define a very important class of rings called Noetherian rings. Okay, so these rings are named after a mathematician called Noether. Who did very important fundamental work in commutative ring theory. So Noetherian rings are named after this mathematician who lived about 100 years ago. Okay, so Noether did a lot of work that we are discussing in this course. Okay, so let me go ahead and define this. This is something that would seem very natural after all these concepts that we have learned. So let's start with an arbitrary ring. So it's a good time for me to remind you that whenever I am talking about a ring in this course, I mean a commutative ring with unity, multiplicative identity. So let R be a ring and let I be an ideal of R. So first let me define the notion of what it means for an ideal to be finitely generated. I is said to be finitely generated if it is what the name is saying, if there exist finitely many elements let's say A1, An in I such that I is equal to the ideal generated by An. So I've already discussed in some previous video what it means for a collection of elements to generate an ideal. So this simply means that every element of I can be written as some linear combination of A1 through An. So every element, let's say A of I, can be written as A equals B1 A1, where Bi's are in R. Okay, so you are allowed to take coefficients from the ring, but it must be a linear combination of A1 through An. Remember, A1 squared, A1 cubed will also be there, but we don't need to include squares here or any other powers, because you can absorb any other extra powers of A1 into the coefficient. Because it's an ideal, we can always write every element like this. So finitely generated simply means that there is a finite set of elements which generate I, meaning every element of I can be written as a linear combination of this. Okay, so examples are plenty, because almost everything that we have seen so far, in fact probably everything that we have seen so far is an example of finitely generated ideal. For example, if you take Z, every ideal is finitely generated, right? So I'm going to write Fg is short for finitely generated. Okay, every ideal is finitely generated in Z, because in fact it is principal, not just finitely generated, right? There is a stronger statement that's true. Every ideal is generated by a single element. We only need, in fact, that every ideal must be finitely generated, I am saying, but even better is true. In fact, every ideal is principal. Similarly, same holds the polynomial ring over a field in one variable. Okay, so here also every ideal is principal, so every ideal is finitely generated in particular. On the other hand, if you take polynomial ring over Z, here not every ideal is principal. This I did not ever mention explicitly before, and this is an exercise now to check for you. The ideal generated by 2x, 2 comma x is not principal. There cannot be a single element which generates 2 comma x, because you take a polynomial of non-constant polynomial, it will not be able to generate 2. If you just take a non-constant, if you take a constant polynomial, it will not generate x. Okay, so no single element will generate the ideal which is generated by 2 comma x. However, every ideal of Zx is finitely generated. So this is also an exercise for you. It need not be generated by a single element, but it is generated by finitely many elements. In fact, I claim that it is generated by 2 elements. You can check this. So what you need to do is take the smallest positive integer that's contained in a given ideal and argue that that and x will generate it. So this I will leave for you, or that and some polynomial will generate it, I should say. Okay, so this is an exercise, maybe I will come back to this later. So this is another interesting example. If you take, on the other hand, polynomial rings in several variables, here we can't yet make any statement about all ideals. We will do that in a future video, but I can talk about this particular ideal is finitely generated. Okay, in fact, what is true in this ring is that every ideal is finitely generated. That I will mention next time. On the other hand, if you take a polynomial ring in infinitely many variables, okay, this we have not encountered before, and I should define this carefully. I will only say this orally for now. We will not really discuss this example a lot in this course. But what is a polynomial ring in infinitely many variables? Any polynomial is actually a finite sum, but it can take variables from this countable infinite collection of variables. Okay, so then you can naturally define addition, multiplication, just like you define in the case of finite number of variables. In this, the ideal generated by all the variables is not finitely generated. Okay, so this is a good example of a non-finitely generated ideal. So why is this not finitely generated? This is a simple exercise, again I will leave for you. Suppose it is finitely generated. It is generated by, let's call this ideal I. If I is finitely generated, let's say generated by some R polynomials, and let's call this ring R, where F1 through Fr are in capital R, then let n, capital N, be the largest positive integer such that the variable xn appears in F1 through Fr. So why is that such a capital N exists? That is because, remember, each polynomial, though we are working inside the polynomial ring in infinitely many variables, a specific element is a finite polynomial. So it can have only finitely many terms. So it may have x 1 million, x billion and so on, but it must stop somewhere. So f1 is a finite sum of terms. So you can figure out the largest index of the variable that appears in f1, the largest index of the variable that appears in f2, and similarly the largest index of the variable that appears in fr, and pick the largest one and call that capital N. So capital capital N is the largest index of a variable that appears in f1 through fr. But now, because we have infinitely many variables, we can consider the next index. So then xn plus 1 cannot be in the ideal generated by f1 through fr, because remember, when you take an element of this ideal, that means you take a1 f1 plus ar fr, where a1 through fr are elements of r, you cannot introduce a new variable. Okay, you can introduce a new variable, but it cannot just be a single variable. Okay, so this last part is a somewhat subtle exercise, but I will leave that for you. It cannot be a single variable. So in other words, f1 through fr cannot generate the ideal I. So however many you take, if you take only finitely many, that finite set of elements cannot generate the ideal I. So it is not finitely generated. Okay, so now let me end this video by giving you the main definition that I want to discuss in the next video. A ring R is called Noetherian. Okay, so I will use this word to describe rings where every ideal is finitely generated. If every ideal of R is finitely generated, then I say that R is Noetherian. Okay, so quickly let me give some examples. What are Noetherian rings? Examples of Noetherian rings. Almost every ring that we have considered so far is Noetherian. Sometimes in some cases it is trivial to check this. Of course, Q, R, C are also Noetherian, because Q, R, C are fields. So there are only two ideals, the unit ideal and the zero ideal, which are of course finitely generated. Every ideal in Z is principal. Every ideal in ZX I said is finitely generated, so that's actually an exercise. Every ideal in Rx is a principal ideal. Every ideal in Cx is a principal ideal, which you can check by doing Euclidean division. So these are all Noetherian rings, and we will in fact check that polynomial rings in finitely many variables are Noetherian later. And what is an example of non-Noetherian ring? Something that's not Noetherian. The only example we know is the polynomial ring in infinitely many variables, which of course I can put coefficients to be anything I want. So these are not Noetherian because I have said here that the ideal generated by all the variables is not finitely generated. And we will see one more example of non-Noetherian ring later, but non-Noetherian rings are very rare. So that's the takeaway from this. And the most interesting examples that we will study in this course are Noetherian. So let me stop the video here. In the next video, we'll continue our study of Noetherian rings. Thank you.